So we're looking at the, okay, I'm still sharing my screen, great. So we're looking here at the intermolecular forces experiment, kind of the post-lab questions, and we're trying to answer these last few questions about making sense of what we look at. And we have to be careful when we do these, because it's these last where we have to do submissions. It's not going to tell us right away if we got it right or wrong. Someone is actually going to download these. So we want to make sure we're putting the proper thought into this. And essentially, we're doing puzzle solving, essentially. We're doing murder mystery, but with chemistry. We're doing chemistry mystery. So the way that I think about the propanol is I look back at our previous compounds, and I notice we've got the 1-propanol in this set, and we've got the 1-propanol in set 2. Set 2 and set 4 have 1-propanol. And then the problem just becomes identifying which peak corresponds to 1-propanol, so we can make some prediction about what the peak for 1-propanol would look like. And the reason I just started recording office hours, sorry I forgot to do it earlier for everyone listening. The thing I wanted to point out was this set is really easy to kind of start looking at. This propanol set. And the reason is because, and I'm going to draw some stuff on the board. And switch over to board view. So the reason the propanol set is nice to look at first. It's compound set 2. You've got propanol, butanol, pentanol. Right, and if you look at my board, you'll notice these 3 compounds look really similar, right? They all have the same OH group, so they're going to have the same functional group. They have a difference in mass, and that's going to and they're also, not because they have a difference in mass, but because they have a difference in surface area, they're also going to have a difference in their London dispersion force. And when we're thinking about boiling, we're going to be thinking about the energy we have to put in to overcome gravitational effects and intermolecular forces effects. So when I'm predicting which peak is going to be first between these 3, I would predict propanol has the lowest boiling point and pentanol has the highest. Because they have the same functional group, they're going to have the same functional group. The dipole-dipole and the hydrogen bonding interactions is going to be approximately the same between the 3. So that's not going to have a huge effect. The gravitational effect is going to get larger as we add more carbons on, so that's going to be part of it. And also, as we increase the surface area, which generally follows with mass, but not perfectly, we're also going to have more London dispersion force from having that larger surface area. So when I'm looking at that series of peaks, they don't actually look that good if we flip back to the other screen. So when I'm looking at these peaks, I would say this first peak is likely to be the propanol. Has the lower surface area, it's going to interact with the tube less. It's going to boil earlier. And this larger peak at the end is probably the pentanol with butanol in the middle. And what we need to do for our thinking is we need to do that type of making sense of these chromatographs for each set. And this second set is a little bit more difficult. You notice it's got the pentanol, it's got pentane 2-ol and pentane 1-ol, and then just pentane. And this one's kind of strange because pentane doesn't even show up, so you only get 2 peaks. There's also a possibility that, there's a second peak like hidden inside there, but it turns out things without dipole moments don't show up. So one of these peaks is the 2-ol, one of these peaks is the 1-ol. And we have to look at those differences in surface area and intermolecular forces, dipole-dipole moment, to figure out which is which. And same type of thinking here. This one's easy. Compound set 1 is kind of easy as well. Acetone, butanone, pentanone, just like what we did on the board. The functional groups are the same in these three, and it's that carbon chain length that's really changing. Compound set 4 is the only one that's really interesting. And you'll notice that's because we're actually changing functional groups here. They're all the propyl, so they're all about the same mass. The propanoic acid has that extra oxygen in it, so it's a little heavier. But this one is really not going to be about the surface area or the mass. This is really going to be about the dipole-dipole interactions and which one is going to have the higher boiling point, lower boiling point. And we want to apply all of that thinking together to answering these post-experiment questions. Does that give you more to think about, Caitlin?
Yeah, it does. Thank you.
Great. Okay. So with that in mind, if you take the time to kind of frame those questions in that way, question 6 becomes a snap. You kind of get something that's like 2 peaks because there's 2 things in it, and then just labeling which peak is which. So the next question somebody has, this is one that's come up a lot this week. We're looking at mastery question 7. Problem 3. And you're given a bunch of things and you're said, oh, figure out the angles. Right? And Sebastian, I notice you have a mistake in your angles. And so we're going to go over your 3 together. You've got A, H, and L. And it looks like you got A right. So if we look at compound A, we say, okay, well, how do we draw compound A? It's a string of, and did you actually draw out the Lewis structures for each of these?
Yes.
We get something like this. You can see why we do line drawings, because I'm already tired of writing all these hydrogens in. And if we want to look particularly at this carbon, 4 things. Means it's going to be a 109.5 angle.
Yeah.
And then we have to check the other ones. And then for compound H, so I guess the thing I'll tell you that might not be immediately obvious is if you look at the compound that's on the right-hand side of in the problem, so that's the compound that has H, I, and J in it.
Yeah.
It's this compound. Right, we've got this compound. You'll notice the oxygen doesn't have its lone pair on it. Should the oxygen have a lone pair?
Yeah.
Yeah.
So, yeah, that's another question I had. Like, I guess I was assuming that they just weren't shown on there, on these diagrams. Like, I didn't, but I guess, like, they were actually not there, the lone pairs. Like, if they were there, they would show it in the lab pal diagrams here.
Yeah, so it's one of those things where in our line drawings, when we get further along in chemistry, we often don't put the lone pairs on the line drawings.
Yeah.
But we need to be, and that's because we assume that people who look at these can, you know, when you see this oxygen, you're not going to be like, oh, that's weird, this oxygen only has 2 electrons next to it.
Yeah, I just assumed that it had the 2.
That is the correct assumption. So let me ask you something. What about this nitrogen?
It shouldn't have anything. because shouldn't nitrogen only have 3 bonds to it?
3 bonds and a...
Oh, yeah, and 1 lone pair.
That's going to change the angle you put down in your problem, right?
Yeah, hold on. I'm just going to where I had that written. Yeah.
Right, because the nitrogens still want to have their full valence shell. They still want to have their 8 electrons. So these things are going to have that 4 things attached when we're considering the angles associated with them.
So then would that be a 109.52?
Yes, it would.
Okay.
Now, and what structure did you draw? If you have it drawn, can you show me what structure you drew for SO2?
It's a little,
That's okay.
I was just doing it on scratch paper.
That's fine. Yes. Yep, that's great. No, that's right.
Yeah.
Yeah, but you notice how many things are attached to it.
What was that?
How many things are attached to your SO2? So for people who are watching office hours afterwards, the SO2 that was drawn looked like this. How many things are attached to that sulfur in the middle?
2 oxygens.
And
the lone pair.
Right. So when we're determining the angle around this thing.
Oh, see, so when I was doing it, I wasn't considering the lone pairs.
So this gets to the important difference between electronic geometry and molecular geometry. Right? And electronic geometry determines our bond angles, which are really important. But when we start getting to intermolecular forces, the stuff we're doing, the second half of the week, we really just want the molecular geometry because we just want to know where the nuclei are in the molecule. So I'm less concerned with the fact that there's a lone pair there, and I'm really just concerned with the fact that we've got this bent geometry so that the oxygens are kind of pointing down from the sulfur.
Yeah.
Because if it was 180, non-polar, right? You've got that even electronegativity distribution. But if it's this 120, that's going to be a bent geometry, and that's going to give rise to a dipole moment, and these two things will have very different physical properties. Like the difference between like having something that's 180 or 120, different boiling points, different melting points, all of that's going to change from that change in the intermolecular forces. And this is the right thing.
If they're 180 from each, like in the top drawing, sorry, of the...
Oh, like this, yeah.
Yeah, that one right there. So the geometry was, the angle, is 180.
If that lone pair wasn't there, it'd be a 180 angle.
Yeah, yeah.
Yes, yes.
So when the angle is 180, and does that mean that the dipoles moments cancel out?
It means the bond dipoles cancel out, so you end up with no molecular dipole.
Okay.
Right? Because this is going to be this way and this way, because they're equal and opposite, they'll cancel out. But if it was like carbon, sulfur, oxygen, then you would have it all pointing to one side. Yeah, so it's because of the symmetry of this molecule that would be the case.
Yeah.
And that would be wrong because it should be bent.
Yeah, yeah.
This gets to kind of the big problem we have in chemistry, which is, if you actually had sulfur dioxide in front of you, it doesn't look like this. It's not an S and an O floating together. Like, it's just our trying to represent these really abstract things.
Yeah.
And coming up with, well, this gets us close enough to the answer.
Yeah.
Here, let me
I'm gonna work on
So, following up, we know the pattern for nitrogen and oxygen in terms of the number of bonds and the number of lone pairs. But for sulfur, in that compound K, I don't remember it very well. I don't remember it. So whenever I'm looking at a sulfur compound, and to get the structure right, let's take a look here. It's going to be boom, boom, sulfur, boom, boom. Okay. I don't know how many lone pairs this sulfur should have in order to give it its full valence shell. Now, there are some tricks we can use. For example, sulfur and oxygen are right in the same group on the periodic table, right? All oxygen is right above sulfur. So my hunch is that this is going to have 2 lone pairs. And it's going to look very similar to oxygen. But to make sure, let's go ahead and do the full Lewis structure. So I'm going to have 1, 2, 3, 4 carbons, bringing 4 electrons each. I'm going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens, bringing 1 electron each. And I'm going to have 1 sulfur, bringing 6 electrons. There's no charge on the molecule, so we'll just go with that completely. Now I have to do some math. 4 times 4 is 16. Plus 6 would be 22. Plus 10 would be 32 electrons. Now, in my structure that I've drawn for my kind of like first guess, you'll notice my carbons all have their full octet. My hydrogens have their full duet. So this is looking pretty good, and I'm going to see how many electrons out of the 32 I've already used. I'm going to switch colors to count. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 2, 4, 6. So I have 26 electrons used. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 2, 4, 6. Is that right?
So, yeah.
Oh, I forgot this bond. You see it doesn't have a dot next to it? I knew something was wrong. I was like, that's not enough. 28 electrons used. I knew what the answer should be, so I knew I missed something. So 28 electrons used, which means 4 electrons left. Which means that sulfur, just like oxygen, is going to have 2 lone pairs.
Yeah. Yeah, so when I originally drew it, I miscalculated how many valence electrons there are, and I said there was 30. So then I only had 1 lone pair.
Oh, yeah, okay. Yep, so yeah, getting that lone pair. Do you know how you got 30 instead of 32?
I just completely butchered the 6 plus 16 plus 10.
Oh, okay, yeah.
Yeah.
No, that's why I was really glad you were there with me to make sure I didn't butcher it as well. So moving on to mastery question 8. There's an important misconception that people have. Right, boiling point's going to be related to, well, let's break it down a little bit more than that. Boiling point's going to be related to influence of gravity plus the IMFs. Right, and it's really the mass is going to be this gravity effect. There's this misconception that mass inherently leads to more surface area. Right, so if I have something that's got 1, 2, 3, 4 carbons versus something with 8 carbons, 2, 3, 4, 5, 6, 7, 8, you would look at these two and say, oh, the thing with 8 carbons clearly has more surface area, ergo, more mass, more surface area. But we can have something with more mass and kind of less surface area if we've got a bunch of branching. 1, 2, 3, 4, 5, 6, 7, 8. So this has 8 carbons. It's a lot more massive. But in terms of surface area, it's now about the same size. So it's not necessarily that more mass inherently means more IMFs. It's more surface area means more IMFs. However, this thing, now that these two things have about the same IMFs, because they have about the same surface area, they have no oxygen groups or anything like that, so they don't have dipole-dipole. And surface area only tells us about the London dispersion force. Right, so it's only telling us about the weakest of the IMFs. But this one's going to be a lot more massive, which means when I'm trying to turn it into a gas, like a free-floating vapor, it's going to take more energy to overcome the gravitational effects. In most cases, particularly in chemistry, but in most cases, the effect of gravity is going to be secondary to the intermolecular forces. But of course, you can have these situations where the masses are really different and the IMFs are very similar, and then gravity is going to matter more. Right? So we essentially have situations that are easy to predict and situations that are difficult to predict. If the difference in IMFs is big and the differences in mass is small, clearly the IMFs are going to dominate. If the difference in IMFs is, if the difference in IMFs is small and the difference in mass is big, then mass will dominate, obviously. The place where it gets tricky is if the difference in both is small or if the difference in both is big. If the difference in both is small, the IMFs are probably still going to dominate. So in this situation, big IMFs, big difference in IMFs would dominate. In the situation where the difference in mass is really big, probably the mass is going to dominate. It's not guaranteed because it depends on how different the IMFs. Well, I guess if the difference in IMFs are small, then mass would dominate. If both are small, if the difference in IMFs and the difference in mass are both small, the IMFs are probably going to dominate because in that situation, the effect of gravity is typically a lot weaker than the IMFs. If you do like an energy per mole type calculation, the IMFs usually dominate unless you're dealing with like really huge molecules. So this one, the IMFs would probably dominate. If the difference in mass is big and the difference in IMFs is big, this is just like a total mystery. That one is really hard to deal with. I would have to know exactly how the IMFs are differing and exactly how the masses are differing in order to figure that one out. There's no like general quick idea to it. I don't know if that answered your question. Okay, good. So this also ties into the rest of our thinking in Mastery Question 8 that I talked. I did do a little bit of recording of this earlier in office hours where we really want to slow down and think, well, the first examples we have, the differences in IMFs are kind of not there very much because they have the same functional groups. And so what really matters there is the fact that there's that difference in mass that's going to be significant. And it's only, I think, compound set 4 where you get into this kind of interesting idea of the IMFs are really different when the masses are very similar. Compound ABCD is a little confusing because the functional groups are the same and the masses are the same. And so what matters there is actually the way that the surface area also contributes to London dispersion force, right? You can actually have two things. We'll toss on a third thing for this random example, 2, 3, 4, 5, 6, 7, 8. Right? Here I've got two things where the masses are the same. So, it's not even a delta mass. So we're looking at this first situation. The differences in the IMFs are actually really small because the IMFs for this compound and for this compound is London dispersion force for both. And so the difference in IMFs is small, but the variation in London dispersion force is going to make it so this octane has a larger IMF. It's going to have more interactions because it's got that larger surface area. Okay, so we're shifting our thinking now. And it's actually very closely related to what we're doing here, except for instead of mastery question, we're looking at IMF post lab. Number 5. And the question is such. If a molecule has a stronger dipole moment than another molecule, does it guarantee it will have a higher boiling point? Explain why or why not. And this gets into kind of this comparison of what gives rise to higher boiling point. Is this balance between, I just erased it, the balance between the intermolecular forces and the mass. So let's go ahead and draw something that's got a really nice dipole moment and then figure out if we can find something that's got a weaker dipole moment but has a higher boiling point. So this is one of the compounds we used in the experiment. This is formaldehyde. Oh, I gotta say the right thing or I'm gonna be embarrassed. Oh good, formaldehyde. Oh, all of my O-chemist colleagues would have made fun of me. It's got a very strong dipole moment because you've just got an oxygen, a carbon, and some hydrogens. And we can even look up the boiling point of formaldehyde since I just Googled it. Looking it up on PubChem the same way we did with lab. Let's go to chemical and physical properties. No, where is it? Patents. Wow, there's a lot of information on formaldehyde. Huh, it doesn't have the boiling point. Weird. We'll just go to Wikipedia. So boiling point for formaldehyde is like negative 19 degrees Celsius, right? It boils before, even though it's got a nice dipole moment, it boils low because it's got this low mass. And then all we have to do is think of anything that's got a weaker dipole moment and a higher boiling point, and I'm just going to make something absurd. Super long carbon chain, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. C13H28. Right? This huge molecule, since it's got such a large surface area, is actually going to have pretty significant London dispersion forces. And because it's got such a large mass, it's going to have significant interactions with gravity. And I can go ahead and see, coincidentally, I don't know if this is a common thing, C13H28. I'll just look it up real quick. Oh, and here it has. Oh, wow. That is a boiling point much higher than I was expecting. So this gives you a pretty good idea of how formaldehyde has a boiling point of -9 degrees Celsius, has a really strong dipole moment, but such a small mass, such a small surface area. .33 divides for that dipole moment. Really nice dipole moment. However, if we go look at this tridecane, that's this long carbon chain that I just made, it has a 0 dipole moment. Do you want to just take a guess at what you think the boiling point's going to be, though?
I want to know.
I would have guessed wrong. Just to let you know, I would have guessed totally wrong.
But it's really big, so it's making me guess like 150 degrees Celsius.
Wait, what were you gonna say before you changed it?
200, 150 to 200, something like that.
230 degrees Celsius.
Wow.
Right, and this makes sense when we think about what it takes to boil something. We have to overcome even though London dispersion force is weak, there's still a huge amount of surface area to this molecule that we have to overcome. So there's that. And even though, that's still not going to be a ton of energy, this thing's mass is so big, we're in this situation where we've got the small difference in IMFs, we've got a big difference in IMFs, but we've got a big difference in mass. This last situation here where it's like, well, I don't know, it depends on how it's different. And in this situation where the thing that's got the bigger IMFs has a much, much smaller mass. And the thing that has the really smaller IMFs has a much, much bigger mass. So, yeah. So there's just one example. And you can probably come up with a ton more that aren't this dramatic. But whenever I'm trying to come up with examples, I always like to go to the extremes. Kind of shows it off really well. Yeah, you bet. So the next thing we're looking at is mastery question 8, predicting our order of boiling points, right? And we're really going to be kind of thinking about this same idea of how do the masses compare, how do the IMFs compare? Keeping in mind when we say IMFs, we have to be thinking about 3 things. The LDF, which is the weakest of those to think about. The dipole-dipole, which has a lot of variability in it. And the hydrogen bonding interaction, which is the strongest, but kind of specialized. And we're looking at, did you say AGH?
Yeah.
So AGH, we've got our compounds. I'm going to draw them all kind of next to each other. There's A. Compound G is going to be like that. And then compound H is going to be like that. So here's the things we want to start looking at to start with is, are the differences in mass between these compounds big or small? Turns out they're all the same.
Small.
Right?
Yeah.
It's 0. So we're going to be in one of these two situations. We're either going to, so in either case, the IMFs are going to matter. And So then we say, okay, well, how are the IMFs different? And the first thing we look at is, okay, well, are they going to have hydrogen bonding interaction, our strongest IMF? So we start thinking about the strongest thing first. And we say, well, we've got oxygens, but none of those oxygens have hydrogens attached to them. So we're not going to have any hydrogen bonding interaction. We're not going to have that really polarized hydrogen possibility. We say, okay, well, what about dipole-dipole interactions? We've got oxygen, so we've got that difference in electronegativity between oxygen and carbon, but it's actually the same between all three of these, right? These are all the same functional group. They're all going to have approximately the same dipoles. So even though they have some dipole-dipole interaction, they're all going to be so similar that's not going to have a big effect. And then we say, okay, well, what about the London dispersion force, the difference in surface area? And that one, we've got a little bit more variation, right? This one has the most surface area. This one has the least surface area. And so if we're looking at it just in terms of, well, in this case, the London dispersion force seems to dominate, we're going to say, well, which one has, and the more forces, the more energy it takes. So from that, we should be able to get an order.
So then, yeah, GAH.
That's what I would put.
Yeah. So yeah, I wasn't even thinking about surface area on that, but
yeah,
it totally makes sense now.
Yeah, and it's really, and that's why I wanted to go through it step by step, was to show you kind of the logic process I use. Because these problems are tricky. There's a lot of different things to consider. And having a kind of process for eliminating which things matters and which things don't makes it really approachable. So you'll notice the first thing I did was say, okay, well, how big are the mass differences? And then I went into the IMS, starting with the strongest first and then going down to the weakest. And we can do that, after you do that for AGH, you can do the same thing for BDI and CEF. And kind of keep going through that logical process.